Okay, welcome. We're going to be spending most of the next 2 weeks getting into the weeds about the economics of transformative AI. But before we do, it can be helpful to brush up on some, more general topics in economic theory, which we'll be using again and again. And even if you're already familiar with a lot of them, it might be worth just familiarizing yourself with the notation that we'll use to make sure we're all on the same page. So to start with some pretty generic mathematical notation, um, I'll generally be letting functions be denoted with this open parenthesis dot close parenthesis thing to distinguish the function from the output of the function, right? The function f from the output f that might come from a given input. F is curly C0 if it's continuous, curly D1 if it's differentiable. I don't know why we start with 1 with differentiable instead of 0, but anyway. And C1 if it's continuously differentiable, that is, if its derivative is continuous. D2 if its derivative is differentiable, that is, if it's twice differentiable, and so on. So you can keep iterating, but I think we'll only ever get up to D2. Or C2 at least. Yeah. Recall that if a function's slope is infinite at some point, if its tangent is vertical, then even if it's smooth there, it's not differentiable there. So for example, the cube root function, that's locally vertical around x equals 0. So it's a smooth function in an intuitive sense, but it's not differentiable. If f has multiple arguments, we can denote the kth derivative of the function by this subscript k in parentheses. And then if we want to talk about the lth derivative of that kth derivative function, we can just put the L inside the parentheses there. This will just be the same thing as if we, used closed parentheses and an open parentheses again. Because, we're talking about the lth derivative of f sub k. Now let's say we have two vectors, x and y, that are the same length. These will always be vectors of real numbers. This greater than sign means that the first vector is greater than the second in every entry, strictly greater. A single greater than sign means that the first vector is strictly greater in some entry and at least as great all around. And the greater than or equal than sign just means that, it's greater than or equal in every entry. If x is a vector and y is a scalar, we can just pairwise compare the elements of the vector to that one scalar, right? So just in precisely the same way as above. Unfortunately, something that's a little inconsistent is that if x and y are both scalars, greater than often just means that the first scalar is much greater than the second in some important sense. And I do this too now and then. And yeah, sorry for the somewhat awkward use of notation. Now let's say f is a real valued function. That means its outputs are real numbers. And it's defined on some domain, D. F is bounded above some value v if there's some other value v underline strictly greater than v, such that f never dips below v underline throughout its domain. So I'll denote this with the greater than sub b sign, right? Bounded above v. Likewise for bounded below and bounded between. It's just the same idea and the same notation, subscript b. So for instance, 1 over x, defined on the domain of positive reals, that's always greater than 0, but it's not bounded above 0 because it can get arbitrarily close, right? As x gets large, f of x equals to 1 over x, that'll fall to 0. If we have a set x of real vectors, L-length vectors, it's convex if whenever you linearly interpolate between elements of the set, you stay within the set. It's closed if whenever a sequence in the set converges to something, that something is itself within the set. Okay, so like, the closed unit interval, that's going to be closed because any sequence in it, if it converges to something, that'll itself be within the interval. But the open unit interval there, that's not closed because you can have a sequence like 1 over x again, which converges to 0, and 0 is outside the set. The set's bounded if you can put a box around it, and it's compact if it's closed and bounded. And that's an important property because of the extreme value theorem. That's important for many reasons, but for us, it's important because of this theorem that a continuous real valued function on a compact set attains a minimum and a maximum. We'll very often be wanting to maximize things, like production or utility. So it's good to know when we can. So let's say that's what we're doing. Suppose you want to maximize a utility function defined over someone's consumption of L goods. And you have a budget B to spend. B is positive. And the prices of the goods are positive as well. You want to choose a most preferred basket. So you want to choose a basket that's within this set of most preferred baskets, the set of x tildes that maximize your utility subject to this constraint, that the total that you spend is no greater than your budget, right? The sum of the total that you're spending on each good, that is the price of the good times the quantity that you're buying, that sums the total that you're spending, and that can't be more than your budget. This set of favorite baskets is called a demand correspondence. And it might not be single valued. You might have multiple favorites or none. But we'll often want to have a demand function. We'll want to make things simple and just find a unique maximum and go in knowing that there will be one. And here's what you need for that to happen. So there's this property, strict quasi-concavity. It's something you see in economics all the time, and I feel like not as much outside of it. Strict quasi-concavity means, let's say you've got two distinct, here we're talking about utility, so I'll say two distinct consumption baskets, and let x denote the weakly dispreferred one, x tilde the other one. If you average the baskets in any way, you like that average basket better than that least preferred one, that x, strictly better. So for instance, let's say you've got a favorite temperature, 70 degrees or something, and how much you like the temperature falls and falls as it gets hotter from that 70 degrees or colder. Now, it doesn't have to be strictly concave, right? It might be that looks more like a bell curve where, once you're already boiling, you're basically dead anyway. So an extra degree doesn't hurt much. But as long as it has this property, it'll be the case that, that strict quasi-concavity is satisfied. If your utility function is continuous and strictly quasi-concave, then you've got a demand function. That demand correspondence is going to have some maxima, and it's only going to have one. The proof is pretty simple. We know that maxima will exist. because of the extreme value theorem, right? We assume the utility function was continuous. And when you think about it, the budget set is compact, right? You can put a box around it, the set of baskets that are affordable to you, and it's going to be closed as well. If you've got a sequence of things that are affordable, it converges to something that'll also be affordable. We won't get into that, but hopefully it's intuitive. And the strict quasi-concavity gives us uniqueness, because if you had multiple favorite options, well, any mixture of them would also be affordable, right? Like, if you're deciding between basket A and basket B, one thing you could do is just spend half your money on half of basket A and the other half on half of basket B. So mixing is feasible, and strict quasi-concavity tells us it'll be strictly preferred. So that would contradict the idea that A and B were favorites. Unless otherwise stated, we'll be assuming strict quasi-concavity. So we'll get demand functions. And when we posit an explicit utility function, it'll pretty much always be not just strictly quasi-concave, but strictly concave, which is which is a stricter condition. Not always. So sometimes we'll deal with linear utility functions, or ones that have some linear component. But this will be the rule. Concavity makes things nice and simple. Now, some properties of the derivative of the utility function that it can be useful to keep an eye on are the Inada conditions. Your utility function satisfies the lower Inada condition on some good L if, as long as you're starting from a basket X featuring like positive consumption of all the other goods, how much you like that first unit of good L goes to infinity, as the quantity of good L is going to zero, right? So if you've got some amount of bread and some amount of jam, how much you like that first microgram of butter is going to infinity. It's just delicious. And this will ensure that you always buy at least a little bit of everything. For no matter how expensive that butter is, there's at least some small amount that you find it worthwhile to buy. Strictly speaking, this will only follow given a differentiable utility function, but this will also be something we assume almost always. So don't need to get into that further. Basically, lower Inada condition implies you buy a little of everything. Likewise, it satisfies the upper Inada condition on some good L if, starting from some basket X where you're buying a positive finite amount of all the other goods, you can satiate sort of asymptotically in good L. As your quantity of it goes to infinity, your marginal utility in that one good is falling to zero. So you're not scaling up all the other ones as well. Regardless of, it could be that it falls to zero even if you did scale up the other ones, but that's the condition. And if a utility function is twice continuously differentiable, we say that two goods are complements locally around some starting basket X if the marginal utility of good K, say, increases when you have more of good L, right? So if how much you like having one more pat of butter increases in how much bread you have, we say that bread and butter are complements. And this will be symmetric, so we don't need to talk about the order in which we listed L and K here. We can just say they're complements or they're not complements. That'll be symmetric by Young's theorem. So this second derivative, for it to be defined in the first place, you need the utility function to be twice differentiable. But what Young's theorem tells us is that if that second derivative is also continuous, then you've got this nice sort of symmetric notion of complementarity. Now, all of these conditions actually can change after monotonically transforming a utility function, right? So maybe I should have just started, started noting this at the beginning here. But take the lower Anata condition. Let's say there's only one good. Well, if you always like having more of it to having less, then any utility function with that feature is it's going to be a monotonic transformation of any other. It'll represent the same ordering, the same preferences. But u of x equals square root of x satisfies the lower Anata condition, and the monotonic transformation u of x equals x, that does not, right? So these will always be well defined as properties of utility functions, but it might be a little jarring at first because we're often used to, letting ourselves take arbitrary monotonic transformations of utility functions because those will represent the same ordinal preferences. So these conditions won't really be telling us something stable about the underlying preferences. These are just features of the utility representation. We'll generally be working with the cardinal notion of utility, though. I'll talk a bit about what I mean by that and why we'll do that later in this lecture. But I think these are just useful properties of functions in general to know about. You can also apply them to production functions and whatever else. And we're talking about utility here, so there you go. But yeah, these are properties of functions, and they're not necessarily retained under monotonic transformation. Okay, so let's say we've got a differentiable utility function. We want to find that utility maximizing demand. If you've done first year micro or even the math camp before starting an econ PhD or master's program, you'll get all into the technicalities here and very rigorously go through what are called the Kuhn-Tucker conditions. And I don't know, 99 times out of 100, you can just find that favorite X intuitively. And so that's what I'll do. I don't think I've ever actually used the Kuhn-Tucker conditions in practice. So here are the two necessary first order conditions. First, let's say there are two goods that you're consuming a positive amount of. The marginal utility of spending a bit more on good L, spending an extra $1, say, on good L, has to equal the marginal utility of spending a bit more on good K, right? Because otherwise, you could do better by just buying a bit more of good L, say, if that's the one with the higher marginal utility per dollar, and a bit less of good K. So you're saving $1 on good K. Or you could shift the money the other direction if K is providing more utils per dollar on the margin. So that's the first condition. The second first order condition is that if there are two goods where you're buying a positive amount of good, of the first one, of good L, and none of good K, the marginal utility of spending yet more on good L has to be at least as great as that of spending that first $1 on good K, right? Because otherwise you could just do better by cutting back on L by $1 and buying that first $1 of K. So those are two necessary conditions for an optimum. They won't be sufficient, though. To see why, suppose you have this utility function here where good 1 always gets you 1 util per unit. You just have linear utility in good 1, but quadratic utility in good 2. Suppose the prices of the goods are equal and equal to 1, and you've got $2 to spend. There are 3 budget-exhausting baskets that satisfy the necessary conditions on the previous slide. You could spend all your money on the first, all your money on the second, just, spend $1 on each. Those are all going to satisfy the first order conditions. And when this happens, you just have to compare the utility values manually to see which is highest or which are highest. And here we can see that there are two things that are tied for favorite, spending both dollars on good 1 or both dollars on good 2. You're not going to want to just spend $1 on good 2 because the marginal utility is increasing. So if you're spending the first dollar is just kind of a fixed cost. You're buying this thing you don't value very much, that first unit of good 2, in order to get, hopefully if you're doing it at all, you're going to want to be spending that second dollar to get the even more preferred second unit of good 2. So it's a local minimum rather than a local maximum to spend only $1 on good 2. So you have to compare them manually if there are multiple candidates. But if there's only one, it's got to be utility maximizing. At least it's got to be, given that there is a solution, but we know that there's a solution because the extreme value theorem and the continuity of the utility function will imply that. And as I said, we're working with a differentiable utility function, so definitely continuous. So to put those sort of intuitive conditions to practice, let's work through this simple budgeting problem, which is very closely analogous to loads and loads of optimization problems that we will see in different contexts throughout the next 2 weeks. Suppose you've got your prices, your budget. You want to maximize this utility function here. So this utility function, it's increasing in each good, because even though rho is negative, so the term inside the parentheses, the sum falls as the quantity of each good rises. You're raising the whole big sum to another negative power, 1 over rho, and then the sum falling raises the overall utility. So first, remember that we can monotonically transform the utility function to get something that's easier to work with. So raise the whole thing to the rho to get rid of that exponent on the outside. That'll flip the sign that'll flip the ordering of the baskets because you're raising it to a negative power. So you can just flip it back again by putting a negative here. So you want to maximize this transformed utility function, nice and separable. And you know that you'll want to buy a positive amount of each good because of the lower Inada condition. See that? Rho is negative. So, let's say it's -1. As XL is going to 0, the derivative here, that's going to, it's like -1 over x squared. So it's going to negative infinity as XL is going to 0, and then we're negating that. So overall derivative of the transformed utility function is going to infinity as XL is going to 0. So we're only going to have to think about that first of our first order conditions. What has to obtain when you're buying a positive amount of each good. What has to obtain is that the marginal utility of spending on each good is equal. And that marginal utility of spending on a given good, on good L, that'll be the marginal utility of good L itself, that's the numerator here, divided by PL, because for every dollar you spend, you only get 1 over PL units of good L. So this is utility per unit, 1 over PL is the number of units you get. That's going to equal a common value for all the goods. Let's call it lambda. So rearrange this identity to get an expression for good L as a function of the prices, the substitution parameter here, and that's the rho and your lambda. Subject it to the budget constraint. Of course, you'll want to exhaust your budget. You can't spend more. So sum term 7 across the k's. This is what you get. And then you can pull this constant outside the sum. Solve for it, and plug it into expression 7 to get a closed form expression for XL. So this is how much you buy of each good. And observe that it's proportional to your budget. So this happens to be a case in which whenever your budget doubles, you buy twice as much of each good. Changes in relative prices can get you to substitute between the goods, but just getting richer or poorer can't here. There's no luxuries in this world for you. Here, you just buy, you just spend a constant proportion of your budget on each good. Okay. Before talking about substitution, we'll be working with demand functions. So just a technicality to get out of the way is that you might hope that if you've got preferences that admit a smooth utility representation of some kind, differentiable or continuously differentiable or whatever, you might hope that the demand function, if, given that it exists, given that we've got strict quasi-concavity, that function inherits the smoothness of the utility function. Unfortunately, it turns out it doesn't. And you can get all into the weeds about what exactly you do need to generate a, say, differentiable demand function. But we won't do that. We'll just assume that it works out that your demand function is differentiable. Now, fixing prices, we can just drop them from the demand function. And we can say that someone's angle, I keep using this I here, but it's not really doing anything. Point is, given that we've got a demand function, the corresponding angle curve is the function from budget sizes to demands. Writing that as x of b is abusing notation a bit because this is a new function, right? We're not representing the prices, but hopefully that's clear enough. So for instance, let's say we're just thinking about some particular good. We'll trace out the angle curve for some particular good. Each good will have its own angle curve, and the overall angle curve will just be how the vector of, for all the goods, how it's, how it changes when the budget changes. But let's say we're thinking about the good of trips to Barbados. When you're starving, you don't spend anything on trips to Barbados, and then maybe you get richer and you still don't. But you have cheaper vacations, and then you get rich enough, and then you go, once every couple of years, and you get richer still, and then you have your own private tropical island, and you don't go at all anymore. So you end up getting a hump-shaped angle curve or something. Now, one important property that preferences can have in principle is homotheticity. Preferences are homothetic if they are representable by a utility function, which is constant returns to scale. Remember, constant returns to scale means that if we multiply all the inputs by some common factor, m, then we multiply the output. We multiply utility by m as well. Now, your homothetic preferences will also be representable by utility functions that are not constant returns to scale, right? You can just kind of take any transformation of this. You can take a square root of u of x or something, and then you'll pull out the m. You'll get an m to the 1/2 here. That's not going to be constant returns to scale. So it doesn't need to be that any utility function representing these preferences is CRS. It just needs to be that there is some utility function that can represent the preferences, which is CRS. So for example, the preference is represented by our transformed utility function from the simple budgeting problem before, that U tilde. Those preferences are homothetic because they can also be represented by the original utility function U, which was clearly CRS. See that? If you multiply XL by M, some common M for all the L's, you've got an M to the row inside the parentheses, which you can pull out, and you're raising it to the 1 over rho on the outside. And so the original utility function gets multiplied by M if all the goods get multiplied by M. But that's not true of the U tilde, right? Going back here, for this U tilde, multiplying all the goods by M, you multiply U tilde by M to the row, not by M itself. Now, homotheticity is an important property to really sharpen up our intuitions about, because it's really commonly assumed for simplicity in lots of macro, and especially I think in growth, and it's false. So I think it can really lead us astray. Now, this is a bit of a hobby horse of mine. I think homotheticity leads us astray more than the average economist, I think. So we'll be hearing a bit more about this than you probably want to over the next 2 weeks. But that's not the hill I really want to die on. The point is, maybe over small ranges, if you're thinking about small economic fluctuations, people aren't getting that much richer or poorer, and homotheticity is a reasonable approximation. I don't think that's true, but I mean, I can see the case for that. The hill I want to die on, though, is that when we're thinking about really different worlds in which we're all perhaps much richer, at least many people are much, much richer than they are now, then you really don't want to be invoking homotheticity or leaning too much on a model that implicitly bakes in some assumption of homotheticity in some subtle way somewhere. So, together we'll be unpacking that sort of thing a bit. The fraction of my budget that I spend on food, say, I mean, it's way higher than what Elon Musk spends on food, right? I mean, a world would just, we'd apportion our spending very differently in a much richer world. Okay, so to start making sure we understand the mechanics of homotheticity, we can just start with this proposition. If preferences are homothetic, the angle curves will be linear. So, every time your budget doubles, you'll spend twice as much on everything. Of course, if your budget's 0, you won't buy any of anything. So if that's not obvious to you, then do try to work through that on your own. And I mean, as I noted as we were going through it, demand for each good was indeed linear in the budget in that example from before, that simple budgeting problem, which we just observed had homothetic preferences. We noted this first implication of homotheticity, right? That the fraction of your budget that you spend on each good is going to be independent of the size of your budget. Another implication, though, which is, I think, the main reason why it's so it's such a helpful, but maybe it's temptingly helpful simplifying assumption to use in macroeconomic contexts, is that if people all have homothetic preferences and they're all the same, then the distribution of wealth is not going to change aggregate demands, right? If we're all spending 10% of our budgets on trips to Barbados, well, it doesn't matter if I have 90% of the pie and you have 10% or vice versa. We know how much is getting spent on trips to Barbados. So let's say there's only two goods and you have homothetic preferences over them. And we can define this concept, the elasticity of substitution for you between them, around some price vector P, the vector here just having two elements, of course, is the proportional decrease in your demand ratio, here defined with one on top, that you choose when good one gets more expensive relative to good two by some small proportion. So the idea is, what's the change in the ratio of good one to good two? The proportional change, right? We're dividing by x1 over x2 in the numerator. So it's the how big is the proportional change in x1 over x2 per proportional change in p1 over p2. And since that'll usually be negative, we just put a negative on it. So we're talking about a positive quantity. Right, like if good one gets relatively more expensive, typically we'll buy less of it. And it turns out that whether you put the one on top or the two makes no difference. This is you're going to get the same formula when you work it through. Why assume homotheticity before defining elasticity of substitution? Well, you have to for line 14 to be well defined, because given homothetic preferences, and only given homothetic preferences globally, the ratio in your demand between two goods is going to depend only on the price ratio and not on the price's absolute levels. So without homotheticity, you could say, so someone comes up to you and they say, okay, what's going to happen to the ratio between your consumption of good one and your consumption of good two, given that price one good one gets 1% more expensive in relative terms, relative to good two? What's going to happen to your demand ratio? And you say, well, I don't know, because there's lots of ways that P1 could go up by 1% relative to P2. P2 could stay fixed and P1 could go up 1%. P1 could stay fixed and P2 could go down 1%. Those would all be ways that you could have a proportional change in the price ratio. But they're going to induce different changes in the demand ratio, unless you've got homothetic preferences. Because under homotheticity, there's no wealth effect under homotheticity, right? You just buy 1% more of everything if you get 1% richer. And so, because you can think of the scenario where instead of good one getting 1% more expensive, good two gets 1% cheaper, you can decompose that into good one getting 1% more expensive. That kind of decreases your real budget, but then you get, your budget increases so that now it's kind of as if just good two got cheaper. That second step is going to have no impact on your demand ratio given homotheticity. See that? So elasticity of substitution is going to be defined, but it's only going to be globally defined if you have homothetic preference. Now, there is a generalized definition of the elasticity of substitution, which picks a utility level, or sort of equivalently, picks a bundle and says, well, at that utility level, or at the utility level associated with that bundle, suppose the price ratio changes by 1%, but your budget also changes by just enough to get you back to that same utility level, then under that, under that particular way that the price ratio be changed, what will happen to your demand ratio? We'll generally only be using the concept of elasticity substitution in combination with homotheticity, but actually, I'm not sure that's true. That it might come up elsewhere, and you might come across it elsewhere anyway. So actually, I remember we yeah, I was confused about this a while back, in fact. Yeah. Um, yeah, I mean, I know how much detail we have to go through this example, but let's say good one is twice as expensive, and if it rose by 1%, if its price rose by 1%, your in this example, let's say, okay, so let's say the price ratio grew by 2% because the price of good one rises by 1%, but it's already double the price of good two. So the ratio is going from 2 to 2.02. So, oh yeah, so right, okay. So in absolute terms, the price ratio is rising by 0.02. So proportionally, the price ratio is rising by 1%, right? And suppose that in absolute terms, the way you respond to this is by decreasing your consumption of good one relative to good two, so that that ratio falls by 0.03, and the ratio started out at something I kind of backward engineered so that the proportional fall in the ratio of your consumption of good one to consumption of good two is 2%. So yeah, good one gets relatively more expensive by 1%. Your relative consumption of good one falls by 2%. So what that would mean is that around the price vector 10, 5, your elasticity of substitution equals 2. Yeah. An important threshold that we'll run into over and over again is whether the elasticity of substitution is greater or less than 1. If it's greater than 1 around some price vector, think about the logic here. If P1 over P2 goes up, X1 over X2 is going to go down usually, right? You're going to buy less of the thing that's gotten relatively more expensive. But how much will it go down? Well, if it goes down by more than 1%, if X1 over X2 goes down by more than 1% per percent that P1 over P2 went up, then the ratio of how much you're spending on good one to how much you're spending on good two will go down. So, if good one gets relatively more expensive, there's two effects at play. You might be spending more dollars on good one because each unit costs more and you still like good one. But you might also be spending fewer dollars on good one because you're shifting over to good two. And so if the elasticity is greater than 1, then that second effect predominates. You're shifting over to good two by so much that even though one's more expensive now, you're spending fewer dollars on it. And conversely, if the elasticity is less than 1, then when a good gets relatively more expensive, you're spending more of your budget on it. Yeah, because this is such an important threshold, we have terms for being on one side or the other. We say that two goods are gross substitutes at some price vector if the elasticity of substitution between them is greater than 1 there, and gross complements if it's less than 1. Note that goods can be gross substitutes, but still be complements in the sense of complementarity discussed before. So, it can be the case that, goods are sort of mildly complementary, um, yeah, I don't know. I should have a good example, but like um I don't know, bread and cheese or something rather than bread and butter. Like they can eat, you're not going to eat butter on its own, but you might eat cheese on its own. Um, so how much you like the cheese increases with how much bread you have, but they might still be gross substitutes in the sense that if the price of cheese halved, you would actually spend a bit less on bread and a bit more on cheese or something. I don't know. I mean, that's at least conceivable. Okay. Um, so we've been thinking about one direction of the logic here. We've been thinking about what happens to your demand changes when, what happens to your demand when prices change a bit. But you can run the logic in reverse as well. Before I do that, actually, let me take a moment. Do you have any questions about elasticity of substitution? What it means, how it works, why there's this big difference between the less than one and greater than one cases? Okay. So running the logic in reverse, we can say, suppose that um, suppose you've got a bunch of people, say, that all have the same preferences. And for simplicity, let's say they're homothetic. And suppose the aggregate quantity of good 1 rises 1% relative to good 2. Let's say good 2 stays fixed and there's 1% more of good 1. What's going to happen to the prices? Well, first, what's going to happen to the quantities? Well, if the markets are clearing, everything available will be bought. So everyone's going to actually be consuming 1% more of good 1 relative to good 2, which is staying fixed. Yeah, I was saying, let's just say everyone's got the same demand function. The price change needed to induce that change in demand so that what people are demanding at the new prices actually equals the new amounts supplied has to be 1 over the elasticity of substitution, like percent per percent change in the relative quantities. That make sense? So yeah, it's if the elasticity of substitution is 2, then in order to make it the case that people buy 1% more of good 1 in relative terms, well, they're really substitutable, right? They're really closely substitutable. It's like white bread and whole wheat bread. And so the price ratio just has to change by something less than 1, by a half, in this example, a percent, in order to get people to shift by that whole 1%. So that supply equals demand. Yeah. Let's continue to assume homotheticity, but now assume that there are multiple goods. Instead of talking about the elasticity of substitution between pairs of goods, let's just talk about what it might mean to say that a particular good has an elasticity of substitution around some price vector P. We'll say that that is even well defined in the first place if the preferences are not only homothetic, but if when you take that expression 14 from before, when you take that, take this equation, if you swap in any other good, any k, in place of good 2, you get the same number. And we'll say, okay, that's just the elasticity of substitution for good 1. So you might think, oh, this will only be well defined under like further restrictive assumptions beyond homotheticity. But it turns out this will be defined given our original kind of heroic homotheticity assumption, because if the price ratios between goods other than L stay the same, but L gets 1% more expensive, that is so kind of the simplest case being the price of everything other than L stays the same in absolute terms, but L gets 1% more expensive. Then given homotheticity, the demand ratio will stay the same for every pair of goods that's not L. Um, and yeah, right, exactly. Sorry. So good L got like 1% more expensive. You're going to buy a bit less of good L, and how much more you buy of good K, it's going to be like the same for all K. So that's why the ratios are going to stay the same for every K tilde that's not L. And so you can just ask the question pairwise, what's the kind of elasticity substitution between L and K or between L and K tilde? And you're going to get the same number given homotheticity. It doesn't have to be obvious, but it turns out that that's true. And so we can just talk about what's the elasticity of substitution for good L around some particular price vector.
So
Yeah.
I'm actually looking for that. Is there somewhere I can see or a simple reason that turns out to be true? Because I feel like I can think of a homothetic function that might not be true.
Yeah, it's a good question. So the reason why I was sort of pausing was because I also wasn't sure how this worked on the fly. And I think I was careful when putting this together, and also I should have maybe added the appendix explaining it. But yeah, can we think about this? What's the function you have in mind?
So it's like a nested CES. You've got a CES outer nest and then two CES inner nest. And then
and they're all CRS as well?
Yeah. And so the full thing's homothetic and all the input. And then if I take, say, 1, 2 in the first nest, then like 3, 4 in the second nest, and I increase the price from good 1. Then
Wait. Sorry. So you've got this nested CES between these two things.
Yeah. Then imagine B is the one we're increasing the price of. The BA, like the AC and the CD quantities, the demand ratios could be different in their changes, no?
Maybe, but I'm not sure I followed. Could you spell that out again?
Yeah. Like if B and A is super substitutable within their nest.
Okay, these are very substitutable.
Yeah, and then let's say the outer nest, like the A, B, and yeah, exactly.
These are very complementary.
Sure. Yeah.
Okay, and then we're asking what happens when the price of
B always.
the price of, let's say B,
Yeah.
goes up by 1% or something.
Yeah.
Okay. And you're saying
Yeah.
we will buy
1% less of it.
what Dan's pointing out is that it seems like we'll buy less B and less A. But we'll buy more
Complementary on the outer nest, right? So more A and B if we're increasing the price of B.
But if we're increasing it, I mean we're spending more.
Yeah. So the shares are higher.
So yeah, these are complementary. It's like left shoes and right shoes. So if left shoes get more expensive, you're not going to shift over to right shoes. You're just going to increase the fraction of your budget you're spending on left shoes rather than right shoes. But we're going to shift a lot over to A in this pair, right? And So yeah, this is going to be very substitutable. You're going to shift over to A a lot. And maybe you're not going to change much what you're spending on C or D, or how much C or D you're buying, because you have basically just as much of this aggregate as you had before, right? So you split it the same way. Yeah, that does seem right. I think I probably just was iterating this at some point, and I was like making the assumption that yeah. Thanks for flagging that. Because like in these CES functional forms, you can just talk about the elasticity of substitution, because there everything's nice and symmetric. So that's what I was hoping to move to. But I think I'm gonna have to add another assumption on the previous slide. Because I mean, I don't know what I was.
Yeah, I mean, I think
thinking.
it seems
Yeah.
like it seems like it's true if like you take one CES nest as a good. So like within one CES function, you could have arbitrarily many goods and it's going to be true.
Well, but so maybe you need CES for it or something rather than just homotheticity. Yeah.
Then everything else just needs to be a single composite as probability, which means you need something like separability.
Yeah, okay. Well, something that does the trick and might be more than you need, more than separability, is but anyway, is constant elasticity of substitution. So yeah, your demands exhibit constant elasticity of substitution if it's the case that, like, for any good, if you increase the price of that good by 1%, the amount of that good that you buy falls by some constant percent, and the amount that you buy of everything else also rises by that same proportion, and that's the same for all goods. And it's the same regardless of like what price ratio you're starting out at. It turns out that your demands are going to be CES precisely if for some elasticity, some epsilon here, which is going to stand for the elasticity of substitution, which is going to be positive and not equal to 1. And some vector, so as long as the number of goods you have, strictly positive, adding up to 1. The preferences can be represented like this. Now, elasticities of substitution can also be 0, 1, or infinity. And in those cases, CES demands are still well, or the utility functions that can give rise to CES demands are so well defined. We'll see them on the next slide. Something to just flag as a technicality is that for demand bundles that have a 0 in symmetry, technically this expression is undefined if the elasticity of substitution is less than 1, because you're raising 0 to a negative power. But the limit will be well defined. The limit as x goes to 0 will be 0. And we can extend the definition of a CES generating utility function accordingly. Sorry, I guess it's coming in 2 slides, those edge cases. Before we get to that, one kind of helpful transformation is to define something called the substitution parameter. That's typically written rho. It's just the elasticity of substitution minus 1 over the elasticity of substitution. All right, so we can just rewrite our CES utility function like that. And hopefully this is looking pretty familiar. This is basically just the utility function we had in the simple budgeting problem. The one thing it has that we didn't have before are these ALs. But if the ALs are all the same, if they're all equal to 1 over L, then they're all, there's elements. So they're going to add up to 1, which is what we need. And then you can just pull out that L to the 1 over rho, and that's just going to be a monotonic transformation, right? You're just multiplying it by constant L to the 1 over rho. So the simple budgeting problem is just kind of a mild special case of like all CES utility functions with negative rho. So it's quite restrictive, right? Like the assumption of constant elasticity of substitution. It's not literally picking a utility function, but it's almost, rather than a condition on a function, it's almost just like identifying a function. Now those edge cases are maybe helpful for building intuition. If goods are really hard to substitute, if the elasticity of substitution is 0, or the substitution parameter is negative infinity, the utility function is just going to be the minimum of the goods with these kind of weights A. So this would be this is something called Leontief preferences, but this would be like the left shoes and right shoes case, right? In the case of left shoes and right shoes, your utility is presumably just the minimum of how many you have of the left shoes and how many you have of the right shoes, and so the A's you can just set equal to a half. But you could also have similar preferences for like bicycle frames and wheels, in which case you're going to have you want the weight on the wheels to be double the weight, or the other way really. You want the coefficient on frames to be double the weight on wheels. And so a sub frame will be 2/3 and a sub wheel will be 1/3. That intermediate case where the elasticity of substitution is exactly equal to 1 corresponds to the rho equaling 0. Just remember, rho is elasticity minus 1 over elasticity. It's also called Cobb-Douglas. It'll just be, you multiply all the goods together and you raise them to powers. The powers add up to 1. And the infinite substitutability case where rho equals 1 is the case of perfect substitution where you just add the goods up. In some sense, in the perfect substitution case, the goods aren't even really different. I mean, at least as far as your preferences are concerned. Yeah. So let's call this transformation thing the substitution parameter and rewrite a CES utility function accordingly. No, we already saw that. Okay. You can do all this in sort of a continuous space of goods as well. Right? You can have a kind of maximum index good big L, where L can be finite or infinite. And then these weights, hey, now you have to integrate to 1 rather than summing to 1. Otherwise, everything is analogous. And note that because the elasticity of substitution has to be defined for it to be constant, at least on our kind of, without that wrinkle we noted before, preferences have to be homothetic for there to even locally ever be an elasticity of substitution. So they certainly have to be homothetic to be CES. But homotheticity does not imply CES. CES is much more restricted. All right. Well, let's apply this to another kind of class of problems that we'll see a bit of, and that you see a lot of kind of throughout economics. Dynamic budgeting. This is not very dynamic, but it's sort of a little bit dynamic. Let's say you've got a budget B and you can buy period T consumption for periods 1, 2, 3, and so on. What's the cost of consumption in period T? Well, money that you invest to period T earns interest. It's multiplied by RT. If you spend it at time 0, you don't earn any interest, so you just get one sort of $1 per dollar. But RT could be less than 1 if you earn negative interest, typically, hopefully, occasionally. So yeah, this is going to be equivalent to static optimization, like static budgeting, given a set of goods called like T, and price is 1 over RT. If every dollar you invest to time 3 turns into $1.7 or something, then, or if every dollar you invest to time 3, it turns into $2, then the cost of a unit of time 3 consumption is a half relative to the cost of time 0 consumption. If you discount the future at on some schedule, some arbitrary schedule, that's fine. That's just kind of like the DFs, the discount factors are kind of like the weights, the A's that we were seeing before. The first order condition is going to be very familiar. Given that you're spending a positive amount at every time, the marginal utility per unit of consumption at a time divided by the price has to be equal. So there shouldn't be a slash. Because you're dividing by the price, but the price is 1 over R. Is there any chance you could make notes of mistakes just so I can, yeah, and I'll do the same. Yeah. So yeah, there's nothing really dynamic about this problem at all. It's a static budgeting problem, but where we're thinking about the goods at different times. And if you'll receive a stream of income that you can't all just allocate from the beginning, that can change things, but it doesn't if you can borrow against your future income at that interest rate that you can earn if you're kind of moving money the other direction. It'll just be equivalent to a static optimization problem again, but where like your starting budget is the sum across time of the income you'll be getting at each time, but divided by R to get the amount that you could, the amount you'd have now if you borrowed against it at the interest rate. Yeah. Yeah, obviously can be continuous as well. Now, as we've seen, the reason why we in many contexts can take monotonic transformations of utility functions is that the bundle that maximizes your utility also maximizes any monotonic transformation of that utility function. But if a consumption path maximizes your sum over time of discounted flow utility, it doesn't generally maximize your sum over time of discounted monotonically transformed utility. It will if this transformation is an affine transformation. So if you just, if you change the utility function to say, actually you get like 5 more utils at every point in time, no matter what you buy, that's not going to change what the optimal sequence of consumption levels to buy is. And same, if you just kind of like rescale the units by A, that's not going to change what's optimal. But you can't change the curvature within each period. What that means is that flow utility here is a cardinal concept rather than an ordinal one. Now, overall utility is still ordinal here because like the consumption stream that maximizes your overall utility over time rather than your flow utility. Well, it'll also be what maximizes that, that original representation of your overall utility to the third power, say, right? But you've got to be transforming the whole stream, not just the flow utility period by period. Does that kind of make sense? Do we get that or not? Should I explain it? Like, let's say at first, let's say there's only one good to make things really simple. I mean, at each time, and which is what we have been assuming. And you start out with like the utility function as it's log. So you want to maximize log of consumption now plus discounted log of consumption next period plus discounted log of consumption in the third period. You're going to want to do some smoothing because if you have any period where you don't consume anything, then you have like negative infinite utils in that period, right? Like the log, as consumption goes to zero, that's really painful. So even if the interest rate is like really low, even if it's negative or something, you're still going to want to put some aside to make sure that you have at least something that you're consuming every year. And then, but if you take a monotonic transformation of log, like just say, let's say you're still linear in each period, then you no longer have this reason to smooth, and you just kind of pick whatever period offers kind of the most utils per dollar given the interest rate, and you spend everything in that period. Okay, so flow utility is a cardinal concept. The curvature of flow utility around some consumption level can be described, among other ways, by something called the inverse elasticity of intertemporal substitution. We'll call it eta. And it can depend on how much you're consuming. It can, depend on where in the function you are. The intuition for this formula is so for starters, I guess, per absolute increase in C, marginal utility is going to fall by like u prime of C, because marginal utility is u prime of C. That's the first derivative. So the rate of change of the derivative in C is going to be the second. And so per proportional increase in C, the marginal utility is going to fall by, that second derivative times how much C you're starting out with. Because 1% of the larger number is bigger than 1% of the smaller number. So that's the absolute amount at which the first derivative changes. And so by what proportion does the first derivative change? Well, you divide by the level. Right? So that's why we're dividing by u prime. So, yeah. In other words, we're saying if consumption goes up by 1%, then your marginal utility falls by eta%. Make sense? If your consumption goes up by 1%, your marginal utility, the slope of your utility function, consumption, falls by eta%. So, 2% or whatever. Note that, affine transformations of your utility function won't change this formula. Because, an affine transformation, as we saw before, is one where you take that original utility function, multiply it by some a that's positive, and add some b. Well, adding the b won't make a difference to the derivative because the constant b will just fall off. Multiplying by a, that'll just multiply the derivative by a, and it'll multiply the second derivative by a as well. So since we're dividing the second by the first, the a's will just cancel. So that affine transformation is not going to change the inverse elasticity of intertemporal substitution. It's sort of intuitive, right? How curvy the function is, it's not going to depend on how much you shift it up or down, or how much what tick marks you put on the axes. Any questions about this concept? Okay. Now, if that inverse elasticity of intertemporal substitution is independent of the consumption level you're starting at, so no matter how much consumption you start with, it's always true that every time you increase your consumption by 1%, your margin utility falls by like 2% or whatever. Then we say your utility function is isoelastic. And if it's isoelastic, with that inverse elasticity of intertemporal substitution denoted by eta, it's got to look like that, or be an affine transformation of something that looks like that. It's going to just be the log function in the case where eta equals 1, or it's going to be that ratio otherwise. We're going to call this the standard form of an isoelastic utility function. Yeah, note that it satisfies the anodic conditions for any eta that's greater than 0. So in the eta equals 0 case, you've got just c to the 1. That's, utility is just a linear consumption. But otherwise, you've got like c to the 1/2, say, that's the square root, or c, if eta is 2, you've got like negative 1 over c plus a constant. In all those cases, you satisfy the lower anodic condition. Vertical utility function around 0 consumption, which means you're going to want to spend a little bit at every time. So yeah, I mean, you can look this up or whatever, but it's good to get a little bit of intuition. So the eta equals 1 central case of log utility, I'll see what a log looks like. At 1, log of 1 equals 0, right? Log of something less than 1 goes down to negative infinity. And it rises without bound, but ever more slowly as c goes to infinity. That's the log case, the eta equals 1 case. For eta less than 1, you're going to get utility not going to negative infinity, but going to some negative number that's finite. For eta, this is the eta less than case. Okay, so for eta equaling 1/2, it'll look kind of like a square root. It'll always equal 0 in standard form. Utility will always equal 0 when consumption is 1 unit. But lower eta, sort of less diminishing partial utility, will have higher utility in any given consumption level. And for eta greater than 1, you have an upper bound to your utility, but not a lower bound. As utility goes, this consumption goes to infinity, at the same time, utility goes towards some ceiling. And you can see what the ceiling is, right? The ceiling, as c goes to infinity, if eta is greater than 1, this expression is going to 0. And so the limit's going, that ceiling is going to be -1 over 1 minus eta. Or 1 over eta minus 1. So this is just CDS, right? Take an affine transformation of that standard form isoelastic utility function. So your goal over 2 periods is to maximize this, right? Your discounted sum of flow utilities, and that's going to be a monotone transformation of that, because you can just divide by the sum of the discount factors. Now you've got these two weights that add up to 1, right? And 1 over 1 minus eta, well, if eta is less than 1, this is positive, that's positive. So you preserve the sign. If eta is greater than 1, then removing the 1 over 1 minus eta flips the sign, but raising it to a negative power also flips the sign. So either way, it's this thing that looks much more recognizably CES is a monotone transformation of our like dynamic budgeting problem. And the elasticity of substitution between periods is precisely 1 over eta. That's why we call it what we call eta, the inverse elasticity of intertemporal substitution. It's just precisely the elasticity of substitution, but where the goods are consumptions at different times. And of course, you can think about continuous time just like before, you could think about a continuum of goods. So these are all the same thing. Rho being less than 0 is like elasticity of substitution less than 1, which is like elasticity of intertemporal substitution greater than 1, and so forth. All right, so just to make sure we haven't completely glazed over, let me just ask you 2 questions. Let's say the interest that you can get, the number of kind of units of consumption you can get in time 2 per dollar you put aside today. Suppose that goes up 1%. What happens to that ratio? You're not getting any future income, or you've already borrowed against it. B is your budget. Well, and by how much? So let's think about this. R2 going up by 1% is like what happening to the price of consumption in good 2? Decreasing by 1%. Yeah, so the price has fallen by 1%. And this here is the ratio between how much you're spending on time 2 and how much you're spending on time 1. Right? So yeah, okay, so now I'm the one that's brain fried. Give me a second. So just hold your horses. So if good 2 is getting 1% cheaper.
Surely just be exactly, yeah.
Yeah, that's what you were saying. I mean, is what Miley? Melee, yeah. The elasticity of substitution governs the ratio of purchases, right? But B minus C1 is not the amount that you purchase, it's the amount that you spend.
Which should be the same thing. Oh, I guess the thing is that your price went up by 1%, but not necessarily the relative price.
No, that's not what's going to matter. That's not what matters. The price falls by 1% for good 2. The B minus C1 over C1, the thing to notice, even though I'm going blank here, is that the B minus C1 is like P2 X2 over P1 X1. Because you spend C1 in period 1, you have this much left over, right? But you don't translate that into period 2 consumption immediately. You have to pay right for it. So if the price of good 2 goes down by 1%, and the relative demand for consumption in the second period goes up by epsilon%, then this whole thing will should rise by epsilon minus 1%. I'll have to figure out why I'm I should have written it. I'll add it to the slides. But anyway, that's the idea. Yeah, okay, good. Zach says so. So there you go. And if your budget gets here's an easy one. If your budget gets 1% bigger, what happens to the fraction of your budget that you consume in period 1? That's unchanged, right? Great. Because this is a case of CES, which is a case of homotheticity. Great. And yeah, the answer to this question is going to be independent of B for the same reason. Right. Even though it took us a while to figure out what the answer was. Doesn't matter what budget you're at because of homotheticity. All right. Well, there's a recap slide for you to for me to leave up there, but thanks for letting me go a few minutes over. And yeah, see you tomorrow.